Welcome to this explainer. I am absolutely thrilled you're tuning in today because we're going to demystify the incredible physics of light and lenses. I mean, have you ever stopped to wonder how a simple, curved piece of glass can manipulate light to help us peer into the craters of the moon or just read the fine print in a book? Actually, your own eyes are literally utilizing these exact physics right now just to watch this. So today we are going to master the fundamental rules of spherical lenses and the lens formula.
All right, so here's our roadmap for today. We'll meet the spherical lenses themselves, map out their physical anatomy, and establish the rule of sines. Then we'll dive right into the lens formula and finally wrap the whole shebang up with magnification and power. Let's get into it.
Section 1. Meet the spherical lenses, the real protagonists of optics.
Okay, let's dive into this clear physical dichotomy between our two main lens types. A lens is basically just a transparent material bound by at least one spherical surface. First up, we have the double convex lens. If you picture a classic magnifying glass, you've got it. Notice how it bulges outwards? It's thicker in the middle than it is at the edges. And because of that specific shape, it converges light rays, bringing them all together to a concentrated point. On the flip side, we have the double concave lens. This one curves inwards, kind of like the entrance to a cave. It's thicker at the edges and thinner in the middle, and it does the exact opposite thing. It diverges light rays, spreading them out. Understanding this fundamental physical difference is absolutely crucial. It's the key to everything else we're going to talk about today, because it entirely changes how light behaves when it hits the glass.
Moving on to Section 2, Anatomy of a Lens, Mapping the World.
So before we can really navigate this optical world, we need a shared vocabulary. First up is the optical center. You can think of this as our absolute origin point, essentially the ground zero of our lens map. Every single distance we calculate in lens physics originates right here, dead center of the lens. It's the vital anchor point for all the math we're about to do. Next up, we have the principal focus. Imagine you shoot rays of light perfectly parallel to the center line of the lens, which, by the way, we call the principal axis. Those rays will undergo refraction. For a convex lens, they converge at one specific point. For a concave lens, they'll appear to diverge away from it. And here's the really important detail. The distance from our ground zero optical center to this principal focus is called the focal length, and we represent that with a lowercase f. This focal length is basically the defining characteristic of any lens. It tells you exactly how powerfully that piece of glass bends incoming light.
All right, Section 3, The Rule of Sines, Setting the Mathematical Compass.
Now, this is the new Cartesian sine convention, but don't let the fancy name fool you. It's essentially just a standard XY graph from your high school math classes. The optical center is the origin point, right at 0, 0. Anything measured in the same direction as the incident light traveling through the lens is positive. Anything going against it is negative. Now, because we always place our object on the left side of the lens, the object distance, which we call u, is always measured going against the light. Therefore, your object distance u is always a negative number. As for heights, upward is positive and downward is negative. Think of it just like coordinates on a grid. If your object is standing upright on the principal axis, its height is a positive value. But if the image it forms ends up upside down, below the axis, that height will be negative. Sticking strictly to these graph rules is the absolute secret to keeping our equations perfectly balanced.
So the crucial point is this. Because a convex lens converges light to a real focus on the far side of the lens, in the direction of the light, its focal length is always a positive value. A concave lens, however, diverges light, creating a virtual focus on the near side of the lens, basically against the light. So its focal length is always a negative value. Try to lock that in your mind for sure. Convex is plus f and concave is minus f.
Which brings us to Section 4, the lens formula, the ultimate cheat code.
And this brilliantly illustrates the ultimate cheat code of optics, the lens formula. 1 over f equals 1 over v minus 1 over u. Now, why exactly am I calling this a cheat code? Well, because instead of painstakingly drawing out meticulous light rays with a ruler on a piece of paper, this beautifully simple equation perfectly predicts reality. Remember, u is the object distance, v is the image distance, and f is our focal length. As long as you remember your sign conventions, like u always being a negative number, this single formula allows you to calculate the precise behavior of literally any spherical lens. You can figure out exactly where an image will form without ever having to draw a single ray diagram. It's a real game changer.
Finally, Section 5, Magnification and Power, Sizing Up Reality. Okay, so the lens formula tells us where the image is, right? but the magnification formula tells us what it actually looks like. Magnification, represented by a lowercase m, is the ratio of the image height to the object height. And thanks to the physics of light rays, we can easily calculate it just by dividing our image distance v by our object distance u. So m equals v over u. If your result for m is negative, it means the image has flipped below the axis. You're looking at a real inverted upside-down image. But if your m is positive, the image is virtual and standing upright. This is incredibly useful because it tells you at a glance whether you're dealing with a giant magnified virtual image, kind of like when you look closely through a magnifying glass, or a shrunken upside-down real image that's being projected onto a sensor inside a digital camera.
But let's take a quick step back into the real world for a second. Think about getting a prescription for eyeglasses. When an optometrist writes down your prescription, they aren't exactly handing you a piece of paper with the lens formula scribbled on it, right? So how exactly do they measure a lens for everyday practical application? Well, they use the power of a lens. The formula is P equals 1 over F. So the optical power is simply the reciprocal of its focal length. But there is one massive caveat here. That focal length must be measured in meters, not centimeters. This creates a really interesting inverse relationship. A thick, curved lens with a very short focal length actually has a much higher optical power because it's bending the light so aggressively. It brings the light to a focus very rapidly, so its power is immense.
And the standard unit for this power? It's called the diopter, represented by a capital D. If you've ever looked at a contact lens box and seen numbers like plus 1.50 or minus 2.00, those are diopters. One diopter equals the power of a lens with a focal length of exactly 1 meter. Tying this right back to our sine rules, convex lenses have a positive focal length, which means they have a positive diopter power. Concave lenses have a negative focal length, giving them a negative diopter. And the coolest part, if you stack lenses together, you just add their powers algebraically to get the total system power. So a +2 lens and a -1 lens stacked together simply give you a total optical system power of +1 diopter.
So I want to leave you with a final challenge to apply what you've learned today. The next time you pick up a magnifying glass, or hey, if you wear glasses, take them off right now and feel the edge profile. Is the glass thicker in the middle, or is it thicker at the edges? Based on the physical shape alone, do your eyes require a positive or negative diopter to see the world clearly? Keep observing, keep calculating, and I'll catch you in the next explainer.